All right. So here is chapter 6 review. This was the one about z-scores, lots of z-scores, stuff like that. So looking at the problem right here, the first thing says, based upon the relationship between mean standard deviation and minimum time, is it reasonable to believe that the distribution of 40-yard running times is approximately normal? So as I read that question, a couple things I want you to think about. It says the relationship between the mean standard deviation and minimum time, which means you need to use those three things to answer the question, which I did. Okay, I found a z-score using the mean and the standard deviation, and then I referred to the minimum. So let's go ahead and see what it says here. So my answer is no, it is not reasonable to believe that the running times are normally distributed. So I answered the question because you got to answer the question. So I answered the question. It says that the minimum has a z-score of, and then I use the minimum, I use the mean, and I use the standard deviation, which is exactly what they asked me to use. So I used all of them, and I got a z-score of negative 1.33. Then I used my z-chart to come up with the probability. So it says if the distribution were normal, then around 9.2% of 40-yard dash times would have a z-score less than 1.33. Where did I get that? I got that from the z-chart. You go to the z-chart, you go to negative 1.33, that's what you're gonna see. You're gonna see 0.092, something else, but 9.2%. But then I said, so 9.2% would be less than 1.33, but none of them will be. That's the minimum. So we're not gonna have any z-scores that are less than that, even though we should have 9.2 that are less than that. So that just confirms for us it's not normally distributed. So there's part A. Part B says they give us some information about a person, and they say calculate and interpret the z-score for the player in this position who can lift 370 pounds. So simply found the z-score. My 370 minus 310 over 25. That is 2.4, and then it says to interpret it. So I calculated it, but now I need to interpret it. So interpreting it would be, this means that the player can lift 2.4 standard deviations above the mean. If it was a negative 2.4, it would be below the mean, okay? But it's positive, so it's above the mean. That's what they were looking for on that one. Then part C gives us information for both players, and it says, hey, which one should we pick? So the work that you would do on that is you'd find the z-score for the 40-yard dash for both of them. So I have a negative 1.2 and I have a negative 0.2 for A and B. Then I do the same z-scores for the weights, and we already knew from part B that A has a 2.4 and B has a 2.6. So then you're kind of asking yourself, well, which one do I want, right? Well, what I'm noticing is these two z-scores, 2.4 and 2.6, yeah, they're different, but they're not that different, right? That's a standard difference of only 0.2. Don't get me wrong, B is still stronger, right? But not that much stronger. But when I look over here at these 40-yard dash times, my goodness, A is a much faster runner than B. He is an entire 1 standard deviation away from B. That's significant, right? So when I come to answering the actual question, I'm going to say that B can lift slightly more than A with a standard difference of 0.2. However, A can run much faster than B with a standard difference of 1. So what's my conclusion? The team should select player A. So hopefully that was helpful. If it's not, as always, send me a remind, and I can we can do a conference and get together and go over it, and you can ask me more questions. Thank ya.